So, hello, welcome. We are going to go through homework solutions out of section 7.5. So first up, use a sum or difference formula to find the exact value of this trigonometric function. Now, 75 degrees is not quite an angle that we can exactly find the sine or cosine for based off our standard reference circle. However, I would say that 75 degrees can be expressed as the sum of 45 degrees and 30 degrees, each of which we can find the sine and cosine of. So we set up the cosine of 75 degrees. That's the cosine of 45 degrees plus 30 degrees. Based on our sum formula for cosine, which we could look up, and I'll just copy up here, the cosine of, and depending on where you find it, it could be a plus b, alpha plus beta. I'll just use a and b. The cosine of a plus b is given by the cosine of a times the cosine of b minus the sine of a times the sine of b. There's our sum formula for cosine. So we take the cosine of the first angle times the cosine of the second angle, 45 and 30, minus the sine of the first angle and the sine of the second angle. And now the cosine of 45 degrees is, I accidentally wrote root 5, root 2 over 2. The cosine of 30 degrees is root 3 over 2. The sine of 45 degrees is root 2 over 2, and the sine of 30 degrees is 1/2. So I get root 6 over 4 minus root 2 over 4. We've already got a common denominator, so root 6 minus root 2 over 4, and that's a nice exact value with no approximation. Okay, next up. Use a sum or difference formula to find the exact value of the trigonometric function sine of 11 pi over 12. So similarly, we just want to find two angles that add up or whose difference is 11 pi over 12, and then that we know the sine and cosine of those two angles. So for example, I want to set up 11 pi over 12 as one angle plus or minus another, and I suspect plus will work because 11 pi over 12 is reasonably large. So thinking of using the same denominator of 12, I just need to get 11 of them, so maybe 8 and 3. I could have also done something like 9 and 2, or 5 and 6, anything where I can sort of add these up, but let's check, can I find the sine and cosine of these things? Well, 8 over 12 simplifies down to, I cancel 4 out of both, leaving 2 pi over 3. And 3 over 12 is just pi over 4. 3 pi over 12, 3 over 12 times pi is pi over 4. Both of these are angles that live in the standard reference circle, so I can find the sine and cosine of both of these. I would point out 9 pi over 12 and 2 pi over 12 would also work. Okay, those are things that we can work with quite nicely. But I happened to pick 8 pi over 12 and 3 pi over 12, so we'll go with that. Now the sum formula for sine is that the sine of a plus b is sine a cos b plus sine b cos a. So the sine of 11 pi over 12, that's the sine of 2 pi over 3 plus pi over 4. Following that formula, it's the sine of the first angle times the cosine of the second, plus the sine of the second angle times the cosine of the first. Okay. Checking a standard reference circle, the sine of 2 pi over 3 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is also root 2 over 2. And cosine of 2 pi over 3 is negative 1/2. So we end up with the square root of 6 over 4 minus the square root of 2 over 4. We've still got a common denominator, root 6 minus root 2 all over 4, and there's our exact answer. Okay, this is very similar, but a little bit in reverse. We've got it set up as a sine of something, cos of something, cos of something, sine of something. And 5 degrees and 40 degrees I can't immediately work with. However, this very closely matches the sum formula for sine, which I'm copying again here. So observe that in the sum formula for sine, You have a sine of an angle, cosine of a second angle, and those get switched in the second argument, sine of b, cos of a, which is exactly what we have here. Sine of one angle, cos of a second, and then cos of that other one, sine of the other one, they've switched. I tend to write it by keeping sine first and cos second and swapping the angles. But here we have the angles in the same order and we've swapped sine and cosine. It is the same thing. Which means this very closely, exactly in fact, matches the sum formula for sine. And I end up with the sine of 45 degrees, which is exactly root 2 over 2. All right, so we're asked to find the exact value of a couple different expressions given the sine of alpha is 4/5, the cos of beta is 2 root 29 over 29, but specifically alpha is in quadrant 1 and beta is in quadrant 4. Okay, why would these be handy? Well, the sine of alpha plus beta, it's fine if you write a and b, although if you're taking further math courses, you might want to get accustomed to writing a Greek letter every now and again. This is going to be sine of alpha cos of beta plus cos of alpha sine of beta. I'll use that convention of swapping the cosines and the sines rather than the order of the angles. Okay. So what's the sine of alpha? It was exactly 4/5. What's the cos of beta? It was given as 2 root 29 over 29. But now notice we need the cosine of alpha and the sine of beta, which weren't explicitly given. So we need to find them. Okay, so sine squared alpha plus cos squared alpha equals 1. The sine of alpha was 4/5, so we have 4/5 squared plus cos squared alpha equals 1. That's 16 over 25 plus cos squared alpha equals 1. Subtracting 16 25ths. Common denominator is 25. 25 minus 16 is 9. And this on the left is still cos squared alpha, which means the cosine of alpha is plus or minus the square root of 9 over 25. In other words, plus or minus 3/5. Now, how do I know whether it's plus or minus? Referring back to the beginning of the problem, since alpha is in quadrant 1, that tells me that the cosine of alpha is positive. So cosine of alpha is positive 3/5. I'm just going to write that up at the top here. Cosine of alpha equals 3/5. I expect I'm going to need it later. Okay. Similarly, we're going to need to find the sine of beta. Remember that this popped up from this sum angle formula. We needed sine of alpha and cos of beta. Great, those were given. We also need cos of alpha, which we just found. It's 3/5, but we need to find the sine of beta. Okay, so we need to do essentially the same work that we just did, except instead of trying to find the cos of alpha, we're trying to find the sine of beta. So erase, erase, erase. Okay, but we're going to do pretty much the same steps. We're going to need to know what quadrant we're in, which is going to tell us whether we want to select a positive or negative answer at the end. So working through all that again, sine squared beta plus cos squared beta equals 1. Sine squared beta is what I'm interested in finding out. Cos squared of beta is 4 times 29 over 29 squared. So that simplifies down to just 4 over 29. Subtracting the 4 over 29 gives me 25 over 29. So therefore, the sine of beta is plus or minus the square root of 25 over 29. aka plus or minus 5 root 29 over 29. But we were given that we are in quadrant 4, which means the sine of beta is negative. So I'm going to pick the negative one, negative 5 root 29 over 29. So I'm going to take that, I'm going to put it up here at the top so that I can use it later on. I expect we'll need it several times. Negative 5 root 29 over 29. Now that we have not just the sine of alpha and cos of beta, which were given to us at the beginning, but we also have the cos of alpha and the sine of beta, we can pretty much proceed with the rest of the problem with no further interruptions. Okay, so I'm just erasing all of this work to clear up some space because we're just going to power through and do all 4 problems quite quickly at this point, now that we have the cos of alpha and the sine of beta figured out. So returning back to the sum formula for sine, sine alpha was given, cos beta was given. Cos alpha is 3/5 and sine beta is negative 5 root 29 over 29. Observe that 5 times 29 is a common denominator in both. That's 145. Here I get 8 root 29 minus 15 root 29 for a net result of negative 7 root 29 over 145. Okay. Honestly, once you have completed this step here, you're done with the trigonometry. Now it's just algebra. So for part B, we're going to use the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And we've already figured all these out. Cosine of alpha was 3/5. Cosine of beta was given to be 2 root 29 over 29. Sine of alpha was given as 4/5, and sine of beta we figured out as minus 5 root 29 over 29. So first of all, this minus sign turns that into a plus. Still have a common denominator of 145. And my numerator is 6 root 29 plus 20 root 29 for 26 root 29. Okay. Part C, the difference formula for sine. This is sine alpha cos beta minus sine beta cos alpha. And again, we found all of these. Sine alpha is 4/5. Cos beta was given as 2 root 29 over 29. Sine of beta is negative 5 square root 29 over 29, and cos of alpha we figured it as 3/5. Common denominator is still 145. I have 8 root 29 plus 15 root 29 for a total of 23 root 29. And that's done. And finally, part D, pretty much same business. Tangent of alpha minus beta. Okay, now there is a sum formula for tangent and a difference formula, but I'm going to be honest, I always forget it. I always just use the sine and cosine difference formulas, which is going to take a little bit of space, so I'm going to take it over to the left here. Okay, I'm going to replace that tangent with a sine over cosine, and I'm going to use the difference formulas for each individually. If you don't mind looking up formulas all the time, that's fine. You can look up a difference formula for tangent, or if you just memorize it, but if I'm being totally honest, I never have. Tangent of alpha minus beta is sine of alpha minus beta over cos of alpha minus beta. Now I can use the sum and difference formulas for those respectively. Sine alpha cos beta minus sine beta cos alpha over cos alpha cos beta plus sine alpha sine beta. Note that this numerator, sine of alpha minus beta, we actually just determined in part C. So that was 23 root 29 over 145. We already did that. Now this denominator, it's kind of a mess, but cos alpha is 3/5. Cos beta is 2 root 29 over 29. I have to then add. The sine of alpha was 4/5, and the sine of beta is negative 5 root 29 over 29. So here I have 23 root 29 over 145. The denominator overall has itself a denominator of 145, and I have 6 root 29 minus 20 root 29 for minus 14 root 29. Some algebraic simplification goes a long way here. Root 29 over root 145 can be factored out of both the numerator and denominator and cancel each other out. Negative 23 over 14. So there's part D. Okay, establish a trigonometric identity. All right, so we're going to do this two ways. Okay, first, without any help, just by starting with one side and trying to make it look like the other. Now I have a sign of a difference, so if I use the difference formula for sine, I know this is the sine of the first angle times the cosine of the second minus the sine of the second times the cosine of the first. At this point, however, there are some known values. The sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So 0 times sine theta, well, I don't know what sine theta is. It doesn't matter. Sine of theta times 0 is definitely going to be 0. So this is just cosine of theta minus 0, aka cosine of theta. So observe what we've done. Starting from one expression, we used a sum formula, or a difference formula, I'm sorry, for sine, and then some known trigonometric values. Sine of pi over 2 is 1, cos of pi over 2 is 0. 0 times anything is 0, and 1 times cos theta is just cos theta, and something minus 0 doesn't change its value. So it does not matter what theta is, the sine of pi over 2 minus theta will always simply be the cosine of theta. However, in your online homework submission system, it doesn't give you a way to write all of this out. Instead, it gives you a few possible options, and you're supposed to judge which one is correct. And the way I suggest going through these is go step by step and seeing, have they done everything correctly? So for example, in part A, they appear to be using a difference formula for sine, sine of one angle, cos of another, cos of the first, sine of the second, but they've put a plus here. That's wrong. Okay. So this is not going to be correctly reasoned. I don't need to keep going. If they've made a mistake, then overall the argument is wrong. So it's not A. Okay. Here, they have correctly done a difference. They've replaced the sine of pi over 2 with 1 and the cosine of pi over 2 with 0, which all checks out. So part B appears to be correctly reasoned, but let's not jump the gun here, okay? Let's check the other ones. Here we've got the sine of pi over 2 minus theta is the sine of pi over 2 times the sine of theta minus the cosine times the cosine. They've mixed this up with a difference formula for cosine, so that's incorrectly reasoned. And similarly, part D makes a similar mistake, where they're mixing sum and difference formulas for sine and cosine. So even if they did get the correct answer at the end, that wouldn't matter. The process was wrong. B is the only one that's correctly reasoned. So let's do another one like that. Establish the following identity. So let's start with one side and try to make it look like the other. Well, the sine of alpha plus beta and the sine of alpha minus beta I've got identities for. And notice that what we want at the end of the day is something where there's only cosines and sines of alpha and beta. No sums remain by the time I get to the end. So let's go ahead and use those identities to get rid of the sums inside the sine functions. So the sine of alpha plus beta is sine alpha cos beta plus sine beta cos alpha. Then I need to subtract the sine of alpha minus beta, which is sine alpha cos beta minus sine beta cos alpha. If I distribute that minus sign out, okay, our first term is what it is. I'm not changing this sum from sine alpha plus beta. Then I distribute the minus sign out and I get a minus sine alpha cos beta and a plus sine beta cos alpha, which altogether these cancel, giving me 2 sine beta cos alpha. Well, that's the same thing we were after, just with two terms in reversed order. Okay. So applying sum and difference formulas and then doing some basic algebra got us to where we wanted it. Between the angles alpha and beta, it doesn't matter what they are. The sine of alpha plus beta minus the sine of alpha minus beta is always 2 times the cosine of alpha times the sine of beta. And again, let's check the suggestions that MyLab gives. And what we're doing is we're not just checking that it starts and ends correctly. They all do. We want to make sure that the reasoning is sound. Okay. So for part A, we've clearly replaced the sine of alpha plus beta with this, and the sine of alpha minus beta with this. Again, we've mixed up formulas for sine and cosine. That's incorrect. Regardless of what happens forward from there, incorrect reasoning was used. It's wrong. Okay. However, let's see. Sine of alpha plus beta has been replaced with this. Then I have to subtract sine of alpha minus beta with this here. And now this person, whoever submitted this, has switched their sum formulas and difference formulas for sine. At least they're not using the formulas for cosine, but they are using the sum formula for sine in place of the difference and vice versa. So incorrectly reasoned. Okay. Sine of alpha plus beta now gets replaced with this. That looks good. Minus stays minus, and this is correctly put, and that all looks fine. And let's just check that the last one doesn't quite work. Yep, again, we've got a sine of a sum, and this looks like a cosine of a sum formula. So we've mixed up formulas for sine versus cosine incorrectly reasoned. So part C is the only one that's correct. And notice, by the way, that is essentially exactly what we did on the left. Sometimes, even without the help, you'll figure out the same way that someone else will. There was not a whole lot of option here.